Welcome back to my YouTube channel. My name is Abisha Bangana, and today we are going to be looking at a multimodal edge inference architecture for infant respiratory distress triage via fused acoustic clinical representations. So our contents, the main contents of the presentation, we are going to look at the introduction, related works, the problem statement, what are some of the limitations we worked with, the data sets we looked at, the EDA that we did, what were some of the results we got, and conclusions. So starting from the background, infant respiratory distress is actually the leading cause of death for children under 5 globally, and 97% of those deaths actually occur in low and middle income countries such as Uganda. And over 50% of the emergency resuscitation equipment that would be required or suitable for those cases are actually non-functional in most of the health centers in the low and middle income countries. And there is no calibrated or an edge deployable system that exists for respiratory distress triage. Early detection can reduce infant mortality by 40% with timely intervention. And these were some of the related works we looked at, starting with Zhang et al., who specifically looked at the pediatrics, and not only infants, but even the children as well. And that was actually one of the benchmark datasets that we worked with, which was the SPR sound audio dataset. And then we have Sata et al., who only had audio data sets, and it was a very small sample and did not have any clinical data sets to look at. Then we had Im et al. As well, who only had a one-dimensional CNN plus LSTM dataset model, a model for that dataset, and it was a single modality, which was audio, with the results being 90% with detection. Then we had the Electric Sheep Africa as well, which is the other dataset that we used, though one of the limitations is that it was synthetic and clinical only, no audio involved. So our problem statement, starting from the domain, is that in the hospitals or in the clinical centers in Uganda, there is subjective assessment in that the assessment or the diagnosis differs from one doctor to the next or one clinician to the next, and this can lead to inconsistent diagnosis. And then we have shortage of experts, and you find that the ones that are readily available do not have that level of expertise and can easily miss some of the early signs. Then we have delayed interventions in some cases. For example, maybe you find that the priority is given to other sectors or other wards and not necessarily infants. And this could actually have prevented some deaths in the infants. Then our statistics, which are also worrying, in that the respiratory distress in infants is actually the leading cause. And moving on to the computational problem, we find that we had tabular data where we got the clinical variables from, but then we also had another data set for audio where we got the respiratory sounds from. And we had an issue of class imbalance, where from the clinical data set, the positive cases for respiratory distress were actually only about 2.6% out of the entire data set. And with the audio data set, we had only about 0.5 samples of stridor. And yet this is one of the main features that are required when you want to look at respiratory distress. And another issue that we had was the unpaired sources, since we used two different data sets that were not paired at all from totally different patients. So our research questions and objectives, from the questions, we had 4 major questions and 4 major research objectives. Our questions being, what are the acoustic features that are best characterize infant respiratory distress? And when we look at fusion, is multimodal fusion outperforming single modality models? Which fusion strategy is best or optimal for unpaired modalities? How can predictions be explained in order to gain clinical trust? Then for our objectives, we wanted to extract discriminative acoustic features such as the mil spectrograms, to develop a multimodal pipeline and compare the 8 modalities, which were 4 clinical and 4 acoustic, to implement the lead fusion ensemble and optimize it for edge deployment, and to be able to deploy the best fused model on Hugging Faces. So moving on to our methodology, we basically looked at the data which was gotten from 2 different sources. The clinical data, which was had about 30,000 records, we pre-processed it, had imputed the missing values, extracted 12 clinical features, standardized them, trained the models, and picked the extreme learning model as our best model, which was evaluated based on different metrics such as accuracy, precision, recall, and the rest, and moved on to the acoustic data as well, which had 2,000 plus recordings, pre-processed the recordings, extracted features such as the male spectrograms in 128 bins, and then we trained the models, and our best model was the convolutional neural network long short-term memory, evaluated it on the same metrics as the clinical model, and we had a late fusion ensemble where we had different weights that we assigned to the different outputs from the different models, with the audio having 30% and the clinical model having 70%, with our optimal weight being 0.3. And our final evaluation, though, was done independently because we had unpaired sources, so we could not fuse it as one. We could not evaluate the actual fused model, and then we moved on to deploy. So our model architecture and our mathematical foundations, we had from the audio, moving on to our male spectrograms, then we had the CNN-LSTM, and we computed the acoustic risk probability using those methods. And we also had the ELM on the other side, which after we got the 12 features, standardized them, trained the ELM model, and used that and also got the clinical probability, PC. The acoustic risk probability was PA, and moving on to the late fusion architecture, where we had the the optimal weight of 0.3 with the audio, with the acoustic risk probability, and then the 0.7 with the clinical risk probability. So our data sets, we looked at two data sets, the acoustic data set as well as the clinical data set. Acoustic had less samples because we had about 6,000, whereas the clinical had 30,000 samples. So we actually had to get 15% of the 30,000 samples, and we used about 4,500 samples from the clinical data set. And then with the acoustic, we actually trained our models using the 985 samples. And then from the acoustic data set, we extracted 33 features, whereas from the clinical data set, we extracted 12 features. And to the right, we have the visualizations from the exploratory data analysis, looking at some of the pie chart from the burden level percentage of the high, moderate, and medium. Then we also look at distribution of the delivery mode by the burden level. We had the gestational age versus respiratory rate, and we see that the respiratory rate was actually lower as the gestational age in weeks was higher. So in other words, the infants that were actually born more towards the term of age, that is like 38 to 39 weeks, actually had a respiratory rate that was more in the normal range than those that were born a bit earlier. And then we also had a wavelet scalogram comparison between how a normal breath sound was and wheeze, how a normal wheeze would sound like. Then we also had a correlation matrix between the audio features, and then we also had signal amplitude by the age group. So for our output results and discussion, we looked at the fused model, and we were comparing its performance from the individual models, like looking at the performance of the individual models as well as the fused model, which was better. So when you look at the clinical model, its results were actually higher and gave us better predictions compared to the audio model when it was evaluated alone. But then when you look at the fused model, its performance was actually slightly better with them fused than when they were working individually, with our optimal fusion weight being 0.3. And then we had the dual attribution, whereas with the CNN-LSTM, we had the spectrogram heat map, and then with the ELM, we had hidden neuron contributions, and with our fusion, we had the integrated gradients. So moving on to our model selection, we look at all the models that we did, which were 8, with 4 being acoustic and 4 being clinical. So we start with the ResNet 18 model, which is an acoustic model. And basically what we had was the input of the results. And then we moved on to picking the features, extracting them, and then we had different layers. We had layer 1, layer 2, layer 3, layer 4, before we got the final result, and then outputted a risk score. Then moving on to XGBoost for the acoustic model, we had an input of the acoustic features. Then we had the trees that we looked at from the different features, and then we came down and had them outputted as well. And then we move on to the CNN model, where we picked the audio audio features. Then we had the male spectrogram, then the convolutional 2D layer, which pretty much just extracted the features from the spectrograms. Then the ReLU and max pooling, where all the negative values were moved towards 0, and then we have the fully connected layer, and that the fully connected layer gives us the final prediction. Then we had the CNN-LSTM, and for CNN-LSTM, after getting the male spectrogram and getting the 2D layer, we first reshape, we get the output from the CNN layer, and then we reshape it such it can be understood by the LSTM layer, and then we have the fully connected layer, which gives us the final prediction. And then for the clinical models, the XGBoost, from the audio models, the one that gave us the best performance was the CNN-LSTM. And moving on to the clinical models, we still had XGBoost, where we picked all the 12 features, and then we had them go through different trees, and then we came down and looked at the risk probability before getting the output risk score. Then we had the logistic regression model, which pretty much did the same thing. And then we move on to the ELM model, and for it here we have each feature that was extracted had its own hidden layer that it was given to, and after that they were all calculated independently before they were taken to the last output layer. And then for the JNN layer, in this case, we also had the patient data. Then it came and we first went through the graph construction for each. And then we had the node features as well as the adjacency matrix. And then that was also outputted through different GNN layers before we went to the output layer and got the final prediction. So for our model compression techniques, because for deployment, we wanted to first compress the model such that it can be deployed and have maximum efficiency. So we had two techniques, starting with pruning. And with pruning, basically what we are looking at to improve is the performance and the efficiency. And how we do this is by reducing the size and complexity of the model, by removing some parts. And we pruned it differently from the light pruning, medium pruning, and aggressive pruning. And from the visualizations on your left, you can see that light pruning actually gave us the best results when we look at the accuracy, and also when we look at the fusion, when we look at the F1 score from the fusion. And for the area under the rock curve, we actually had the medium pruning giving us the best results. And then for inference speed, we still had the speed of the final deployed model. We actually still had the original having the best, but after that we had the medium pruned model giving us the next best results. So from there we analyzed that with CNN-LSTM, we analyzed the activation patterns on test data, and with the ELM clinical model, we removed hidden neurons by the beta weight magnitude. And for the second compression technique, which is quantization, here we basically look at converting the high precision models, or what we would call the float 32, to lower precision models such as int8. So with looking at how we had different models, with the audio CNN-LSTM, we instead quantized it to int8. And then with the clinical ELM, we converted it to FP16. So from here, when we look to the left, we have the different performance metrics comparison, and we see that the original actually had a slightly better scores than the quantized final models, but then the difference was not actually a lot, because the accuracy drop was only about 0.36%, and we achieved a 74.6 size reduction, as we see in the model size comparison, which was actually good, from 152.3 MBs to 38.75 MBs. And moving on to our model deployment, where we look at the pipeline, starting from the developer, and then we train the models, the CNN-LSTM and the ELM, and then we save the models after logging the metrics and version control. So we move on. That was from the developer to JIT, which we used as our version control. And then we had From that, we exported the models, and then we saved the quantized models. And then for development, we used Gradio. And from there, for the deployment part, we deployed on Hugging Face spaces. And for the last part of the inline clinician, here it's basically showing how the clinician is going to be using the deployed model. So the clinician, what they do when they have the interface, they run it, and then that retrains the models based on what the model will take in, what it has been fed from the clinician, and it will give output. So basically, the pipeline has 6 basic steps, which is from the training and versioning, quantization and exporting of the models, development of the models, deployment on Hugging Face spaces as a proof of concept access, because before we can get paired models, right now what we have is a proof of concept and a user interaction where the clinicians can interact with the web interface, and then we have the monitoring and maintenance, of course, where we look at the performance with feedback to make it better. And the next one, we look at what our prototype is going to look like from the UI. And this is our TotoScreen. On the left, what is in blue is actually where it takes in the audio as well as the clinical features, or you can upload the recording. And after that, once you generate the prediction, it gives you the image on the right, and it can tell you whether the details you've entered of that infant, whether they are at a high risk of having respiratory distress, or if it's a low risk or a medium risk. And it comes down to explain further why they think so, and how it generated that prediction. So our limitations, some of the limitations, we had the class imbalance, and with clinical having about 2.6% of the positive cases, and then we had Strider having only about 0.5% of the cases out of all the 6,000 plus samples in the audio data. And we moved on to unpaired modalities as well, since the data was gotten from different sources. So evaluation of the fused model is actually impossible, and we also could only do lead fusion, but for evaluation, we have to evaluate the models individually. And then for the domain shift, in that the audio recordings that we have span all the way from 1 month to 18 years, and yet what we are focusing on is actually infants, which is from 1 to 12 months, and our clinical data, it being synthetic and not real world data, so it cannot generalize to actual infants, and that's why transfer learning is in our future works. So as we conclude, we have to see, we talk about how lead fusion is what was required of us. And then the clinical, like I previously mentioned, clinical and acoustic models were evaluated individually. And then optimal performance was achieved by fusing the ELM and the CNN, which were our best performing models from the different domains. And lead fusion ensemble is what was our lead fusion ensemble model is what was deployed on Hugging Face. And what we have in the future planned is the field test at Mulago, such that we can get both clinical and audio data from the same infants, such that we can be able to transfer our learning from the models we currently have, and then to integrate live vital signs for real-time monitoring and improve predictions, and to be able to move from a web interface and have one on the mobile application in low resource settings without having to depend on the internet, and to conduct a study to confirm that the deployed tool will actually reduce the time to treatment instead of increasing it, and how it can help the clinicians in generating their outcomes or predicting their outcomes such that it takes less time. And then we would like to acknowledge the data, the data accessors, or the people that gave us access to the data, that is the Electric Sheep Africa, as well as the SPR Sound Dataset authors, and Makerere University, which is our institution, as well as our supervisor. Thank you very much. This has been Abisha Baingana presenting about infant respiratory distress triage. Thank you.